So section 4.1 is going to go over exponential functions. And let me give you some reminders on some of that stuff by starting out with tables of an exponential function. Now I've typed this one into Desmos, and I actually gave it the same name that the problem did, and then it is h of x equals 2 times 1/4 to the x power. The cool thing about doing it that way is I can type in like a 2, or 3, or 4. Now, depending on how you have things set up, like if I type in a 4, I'm getting a decimal value. But occasionally, you'll see this little symbol here, and that means you can turn that decimal into a fraction. So in this case, that fraction is 1 over 128. Now, not everything's going to be a fraction. If I type in the square root of 2, for instance, so SQRT of 2, then notice I don't have that option anymore. It's just some really ugly number, but it's not able to be expressed as a fraction. Going back here to like 3, there you go, beautiful. Now, that'll help you with the first part of this, filling in this table. You can also do tables off of your graphing calculator. The second part is which graph could this be? And I want to remind you of the basic shapes of these graphs. So let me start by dialing this up to something here. Put in a 2, and there we go, 2. So there's your nice growing exponential function. Nice basic increasing function. And it kind of looks like this. After it crosses the y-axis at this point, 0, 1, it takes off. It gets really, really big, really, really fast. On the other hand, if I play with this some more, I realize that this can get faster or get bigger faster by increasing the base, as increasing this, the a. But what if I decreased it? What if I made it smaller, like something less than 1? Then instead of an increasing function, I've got a decreasing function. And that function can decrease really, really fast. It kind of depends on the base here. But the smaller this is, as long as it's greater than 0, the faster it decreases. So let's put that on our little sheet as well. So that's going to be your decreasing function, like that. And again, it's going to pass through 0, 1. I'm sorry that they're not a little bit more even in height. But let's do a couple more things to these graphs. If I multiply this graph by a negative, so that I was then looking at the graph of y equals negative a to the x, in this case, what's the negative going to do to this graph? It's going to flip it. It's going to reflect it around the x-axis, and it's going to come down like this. And I can do likewise with this graph over here. I can look at y equals negative a to the negative x. So not only have you flipped it around the x-axis, but you're flipping it down here. And I don't know if I need to put the negative x in here if I'm doing this part. Well, it's going to look like this. So actually, let me get rid of the negative here. The idea is that the base here is between 0 and 1. So one of these 4 types of behavior are what you're going to see from your exponential functions. Bringing that back to this, I'm going to ignore the 2 part. There's 2 things I need to look at. One is that this number out front, even though it's a 2, it's positive, and this base is between 0 and 1. So if the base is between 0 and 1, I'm going to have behavior like this or like this. This is positive, this one's negative, so my graph has to look like this right here. So it would be this one right there would be your decaying function. This one's kind of a quick one. It says a to the x equals f of x. And this function passes through the point -1 and 6. So let's do y equals a to the x. And if this graph passes through the point -1 and 6, that means -1 for x gives me 6 for y. Or 1 over a equals 6. Multiply both sides by a, I get 6a equals 1. Solve for a, I get x is 1 over 6. Done. Yeah, that would look right. Yep. Okay. Onward. I'll show you a cute decimal tricks. You can graph these one at a time to figure out which family of curves represents this. But let me rule out a couple of these. These are all x to some positive number. They're putting in the following values: 0.2, 0.5, 1, 2, and 4. But I can rule out a couple of these right away. So for instance, I can rule out this one right here, the second one, because one of the things it has is a decaying function. 2 to some positive value is going to be an increasing function. So I can rule out what I would call graph B here. I could also rule out this one, because all the graphs of this form, 2 to some power x, should pass through the point 0, 1. And this one doesn't. This one passes through a bunch of different points. So I can rule out these two. Now of the remaining examples, remaining 2, then it's just a matter of kind of graphing these things and figuring out which one is which. I did a little wizardry here with Desmos. It's down at the bottom. Here's 2 equals c to the x. And these are your different values of c in the square brackets separated by commas. So you can kind of see that at x equals 1, it passes through, say, this point here, and then the square root of 2 here, and then 2, then 4, and then 8. And it's just a matter of coming back here and lining up and saying, okay, it looks like, yeah, that one looks good, that one looks good, that one looks good. So it looks like this one here, just by comparing things. 2 more little quick ones. So we're going to talk about a very fictional example here. A handsome athletic mathematician and homebrewer adds yeast to his fresh batch of an IPA. So any relationship to, you know, the instructor right now is purely intentional. Mm-hmm. But the important part that you should get here is that you're starting with 120 million bacteria and that it doubles every hour. So let's see here. That means y of x is going to be 120 million, and after an hour, it's going to be times 2. And then after 2 hours, it's going to be times 2 again, and then times 2 again, times 2 again. So really, you're going to multiply by 2 for every value of x here. And the fancy way to do that is 2 to the x power. Now, Darian, did you figure out what they were looking for? Were they looking for an exact number?
No. The person on the website just wrote like a whole long number. I didn't let any.
Okay. All right. So if, for instance, I wanted to figure out how many yeast cells were in my batch of wort, which is what beer is called when it's freshly brewed before you ferment it, y of 24 would be 120 million times 2 to the 24. That's going to be a really big number. It's going to be in the quadrillions. Now, when you do that on your graphing calculator, you're going to get a number in scientific notation. So let me clear out of here. 120 million times 2 raised to the 24. Now you should expect a really, really big number. And if you're looking at this and going, wait a minute, 2.01, that's not a really big number. Well, you got to look all the way down to the right end of this. It's times 10 to the 15th power there. So that's 120, excuse me, no. It's 2.0133, we'll call it, times 10 to the 15th power. That's what that E15 represents. If you wanted to turn that into a decimal value, and I think you should be able to do that, you're going to move that decimal 15 places to the right. So 1, 2, 3, 0, 1, 3, and then another 3, and then 9 more zeros. So that number is millions, billions, trillions, quadrillions would be all the way out here. It's a big number. I'm not sure what they're going to want you to put in WebAssign. I hope they don't want you to keep all the significant digits. Question?
It's not really like how you said billions, trillions, and so on. What's the biggest name?
Well, how about this one? A Google. That's 10 to the 100th power. Or if you want one that's bigger than that, Google Plex is 10 to the power of a Google. And that's the biggest one that I know. That would be gargantuan. Just for reference, so 10 to the 100 power is a Google, and it's spelled differently than the search engine, but the search engine gets its name from this. Because you can search for a Google amount of things on Google, is the thinking. So, but for comparison's sake, the number of particles in the universe, protons, neutrons, electrons, is thought to be around 10 to the 80th. So this is bigger than anything we could even think of, by a lot. So, cool question. Cool question. Hope you enjoyed the answer. All right, last little bit here. Graph this function. They want you to graph y equals 4 minus 1/10 to the x power, but not by shifting. And I want to demonstrate something about 1/10 to the x this way. I'm going to start out by looking at 10 to the negative x. And 10 to the negative x I can write as 10 to the negative first raised to the x. And you remember your little tricks with exponents? What can I do with 10 to a negative first power?
The denominator?
Yeah, put in the denominator, 1/10 x. So these things are the same. Now if I was graphing this, y equals 1/10 x, I kind of know what to expect. I expect a decaying function. And that's going to be the same as 10 to the negative x. Another decaying function. But you can think of it that first form in kind of a different way. So I'm going to shut these off, and let's go back up here. Y equals 10 to the x. Not a big surprise, a really, really fast growing function. It passes through 0, 1. But if I replace 10 to the x by 10 to the negative x, that's going to cause it to reflect around the y-axis. Remember, we did those translations in chapter 2. Reflect around the y-axis? Oh, I get that. Or I can think of it as the decaying function, so I'll shut this off. This, same thing. Now I'll shut this one off. Now what else can I do? Well, to kind of get it more and more like the formula that we were given, which is down here at the bottom, I can multiply this by a negative. What's multiplying this by a negative going to do to my graph here?
Flip it over the x-axis.
Flips it over the x-axis. Spot on, Janae. Yay, bonus points for Janae. So let me shut this off. Now I've got this graph. What if I add 4 to that expression?
And go up by 4.
Should shift up by 4. Bingo. On a roll. And if I just rewrite it as 4 minus this, actually, that x should be on the outside here. Raised to the x. Then this graph should be the same. There it is. So it's the same, these last two. So the thing to see here is that this has a horizontal asymptote at y equals 4. But this is your graph. And it passes through 0, 3. It's kind of like the elbow of that curve. All right, looking good. Let me give you some peace so that you can finish this up. Any other questions or thoughts? Good. Good luck.